Hello students, welcome to the EPG Pathshala. I am Dr. Imtiaz Hassan from Jamia Millia Islamia, a central university. Today we are going to talk on module fluorescence parameters such as factors affecting fluorescence, chemical structure, polarity, viscosity of the solvent, pH of the system, temperature and quencher under the paper techniques used in the molecular biophysics part 2. After studying this model, the student will be able to understand what is the fluorescence phenomena. What is the basic concept of the fluorescence phenomena. Then we talk about the fluorescence instruments, components of fluorescence instruments, how it works, what are the base fundamental principles to work. Then we discuss about the fluorescence spectra, what is the feature of fluorescence spectra, how it appears, and what kind of information can derive from the fluorescence spectra. Then we discuss about the different types of fluorophores, like the extrinsic fluorophores, intrinsic fluorophores, and all these details about all these fluorophores. And then we discuss about the factors affecting the fluorescence, like what are the properties, what are the solvent system, medium, and chemical structure. These are the factors which affecting the fluorescence properties of any material that we will discuss in detail. And then at last we will discuss about the experimental conditions and general maintenance of instruments. So let's start. Let's start with the basic concept of fluorescence spectroscopy. You know that fluorescence is a simple process in which one atoms or molecules are excited by the absorption of electromagnetic radiation, which have certain amount of energy to excite the electron, and then excited species try to relax to its ground state, and in this returning to the ground state it loses some sort of energy in the form of photon, and that is actually termed as the fluorescence phenomena. So fluorescence is relatively highly sensitive technique as compared to the absorption spectroscopy, and if it talks about the magnitude, it having the very high magnitude, 3 order of magnitude as compared to the absorption spectroscopy. So it is measured by generally the exciting a sample at its absorption wavelength, the wavelength at which that sample should absorb the light, and then it got excited. So this wavelength is also known as excitation wavelength or absorption wavelength, and then measuring the emission at the slightly longer wavelength, and that's called the longer or emission fluorescence wavelength. This phenomena is a very short-lived. It is very fast process, and in comparison to luminescence is a longer process. So fluorescence, the average time of fluorescence is 10 to the power minus 10 to 10 power minus 7 second. However, the luminescence is a very longer period. So that's the major difference between the fluorescence and luminescence. And the luminescence leads to the phosphorescence, which having the average time of 10 to the power minus 5 to 10 to the power plus 3, and it's possible only in the triplet excited state, rather than fluorescence is possible only in the singlet excited state. Now we know why we use fluorescence spectroscopy. What are the basic advantages, what are the major advantages associated with the fluorescence spectroscopy as compared to the other spectroscopy. So the first reason to use the fluorescence spectroscopy is its high sensitivity, especially the sensitivity towards the local medium. That a slight change in the medium can lead to the dramatic change in the spectrum, which can easily be detected, like the change of the polarity, change of the hydrophobicity can lead to a change in the fluorescence spectrum, which can give you information about the structure, stability, and molecular environment of any biological molecules. Then this technique is also used to track any biochemical reaction, like a biochemical reaction proceed from reactant to product. So the disappearance of reactant and appearance of product both are simultaneously correlated by the fluorescence spectroscopy, and then you can, by this way, you can measure the process of biochemical reaction, and you can even entrap the intermediate states. It's also used to estimate the local friction of the micromolecules, and then it also help you to track the solvation dynamics of the compounds. Most importantly, it is used to measure the distance between the molecules, by distance between the two molecules, or change in the distance between the two molecules, by the special type of fluorescence that is known as fluorescence resonance energy transfer, FRET. We are going to discuss about the photophysics in the of Jablonski diagram, which is the major principle of fluorescence spectroscopy, and the whole fluorescence methods are based on the Jablonski diagram. You can see here that the different states, like the S0 is greater than the ground state, excited state 1 and excited state 2. Once the light absorbed, ground state converted into the excited state 1, and the further it is excited state 2. Once returning the electrons from the excited state to ground state leads to the fluorescence from the singlet side. However, if it returns from the triplet side, it gives to the phosphorescence. Here you can see here in the conventional diagram that how the absorbance, fluorescence and interconversion occurs in the molecule at the different singlet and triplet states. We are going to discuss about the transitions. A transition occurs when the energy of a molecule changes from one state to another. Example, from ground state to the first excited state. Such transition can be shown on a potential energy diagram. You can see here that the excitation absorption occurs when the radiation causes an increase in energy of the system with which it interacts, and the emission occurs when radiation is produced by the system during a transition from a higher energy level which backs to a lower energy level. We discuss about the frequency of radiation required to promote the transition between two energy level. You can see here that energy level 1, energy level 2 minus energy level 1 it gives the delta energy. There is a difference in the energy which is equals to the h nu. That is, the total energy of a molecule is the sum of the distinct reservoir of the energy. These are the translational energy, vibrational energy, electronic nuclear spin and orientation state. There are different types of light are required to produce different kinds of transition. For example, the high energy lights, the X-ray which causes diffraction, then the visible range light, UV range light gives electronic transition and in the outer shell as well as in the inner shell. However, the IR giving the vibrational transitional and microwave gives the rotational transition. We show you how the fluorescence occurs. Simply you can see here the electrons are at the ground state after absorbing certain amount of energy at its excitation wavelength. The electrons comes to the excited state, then it further comes back to its ground state by releasing certain sort of energy which is actually observed in the form of fluorescence. Some chromophores are quite rigid and flexible, thus have a limited range of vibrational level, and often a vibration energy of excited and ground state do not overlap, so it is not possible for them to return to the ground state by losing its energy as heat. In fluorescence spectroscopy, the energy is lost by a radiative transition. Now we discuss about the fluorescence spectrum. The fluorescence spectrum consists of two major components. One is the excitation spectrum, one is the emission spectrum. So the excitation spectrum is actually give you the information about the ability of molecule to get excited by gaining some sort of energy in the form of radiation. So the excitation spectrum is a measure of the ability of impinging radiation to raise the molecule to various excited state at different wavelength. An excitation spectrum is recording of fluorescence versus wavelength of exciting or incident radiation. It is simply obtained by the fixing the emission monochromator to a particular wavelength and then scanning the different excitation monochromator, which gives you the information about what are the best wavelength to select to get the all molecule or the electron get excited for the fluorescence phenomena. So after excitation, a spectrum looks very much like to the absorption spectrum, because greater the absorbance at the excitation wavelength, more molecules are promoted to the excited state, and of course more emission will take place. So the selection of excitation spectrum is very critical phenomena in fluorescence. You should try to excite any molecule to where it absorb maximum amount of the light, so it will give you the better emission spectra. And energy level diagram showing why the structure is seen in the absorption and emission spectra and why the spectra seem roughly mirror image of each other. So generally, if you found that both excitation spectra and emission spectra are mirror image of each other with respect to the change in fluorescence wavelength. Now we talk about the emission spectra. Emission spectra is the measure of relative intensity of radiation gives off at various wavelength as molecule returns to its from its excited state to the ground state. The emission spectrum is recording of fluorescence versus the wavelength of the fluorescence radiation, and it is obtained by setting the excitation monochromator to a wavelength and sample absorb the scanning of the emission spectrum emission monochromator. Since some of the absorbed energy is usually lost as a heat, so the emission spectrum occurs at longer wavelength than the corresponding excitation spectrum. If an emission spectrum occurs at a shorter wavelength than the excitation spectrum, the presence of second fluorescence species must be confirmed, because in general concept, the whatever the light absorbed at the time of the absorbed during the excitation, certain amount should be lost. That's what the energy of the light should be low, and of course the wavelength is increased, so always the emission maxima is greater than the absorption maximum. If it doesn't happen, it means that there are certain species are present there which may absorbing some sort of the light or may release some energy. The absorption and emission spectra have an approximate mirror image relationship if spacing between the vibration level are roughly equal and if the transition probability are similar. And at last we can say that excitation and spectra are of anthracene. You can see here that the excitation emission spectra of anthracene both are mirror image to each other, having certain absorption wavelength and certain emission maxima. We discuss about the instrumentation of the fluorescence. You can see here that it's having a xenon lamp which is the source of the light, and the light of particular wavelength are selected by the excitation monochromator, which focuses the light to the lens, and that lens focus light to the sample. At the right angle of the sample, emitted lights are collected by the another lens, and which directs this to the emission monochromator, and then light pass to the detector and gives the signal in the form of fluorescence spectrum. Now we discuss about the components of a spectrophotometer. What are the major component of a spectrophotometer and what are the function of each component? So the basic spectrophotometer contains a light source, two monochromator, and a sample holder and a detector. There are two monochromator, one for the selection of the excitation wavelength and another for the analysis of the emitted light. So these two monochromator is used for the absorption and emission, selection of absorption and emission spectrum. And the detector is placed at 90 degree to the excitation beam, because the emission takes place in all the direction as compared to absorption always happen in a unidirectional linear direction. However, the emission takes place in all the direction. That's what, to avoid any absorption phenomena, always detectors are placed at right angle to the excitation light. So upon excitation, the sample molecule fluorescence and emitted in all direction and detected by photocell at right angle to the excitation beam. The lamp source is used as a xenon arc lamp that emits radiation in the UV visible and near IR region, which have sufficient amount of energy to excite the electron from its ground state to the excited state. And the light is directed by an optical system by the excitation monochromator, which allows either pre-selection of wavelength or scanning the certain wavelength range. Once you know the absorption wavelength, then you can directly select the absorption wavelength or excitation wavelength, and then you can collect the emission spectrum, and vice versa. You can fix the emission wavelength and then you can scan the absorption wavelength. In both the way, two monochromator are helping to select the particular lights of the wavelength for the excitation and emission. So the excited light then passes through the sample chamber, and which contains the fluorescence having the fluorescence capacity in the cuvette, and that's what it is detected by using the spectropolarimeter. We discuss about the quantum yield. The fluorescence intensity is described in the terms of quantum yield. that is denoted as the phi f. Phi f is the number of fluorescence quanta emitted divided by the number of quanta absorbed to a singlet excited state, or it is also described as a ratio of photon emitted to the photon absorbed. Quantum yield is the ratio of photon emitted to the photon absorbed by a system given as Kr by Kt equals to tau f into Kr, which is equals to tau f by tau r, where phi is the fluorescence quantum yield, tau f is the fluorescence lifetime, and tau r is the radiative fluorescence lifetime. In fluorescence, there are several fluorescence parameters, in which fluorescence lifetime is one of the major and important component of the fluorescence spectroscopy. This is the another property of fluorescing molecule, that is the lifetime. It is represented in the form of tau of the lowest excited state, singlet state. The lifetime of excited state is defined as the average time of molecules spent in the excited state prior to return to its ground state. Generally, fluorescence lifetime are near 10 nanoseconds. It's very short lifetime, and that gives the quantum yield of fluorescence and tau r. So actually the fluorescence lifetime is related to the quantum yield of the fluorescing molecule, and they have a particular relationship which described as the quantum yield in the form of phi equals to kf divided by kf plus kd, and that's all equals to kf into tau. So where kf is the rates of fluorescence and kd is the radiation rate of deactivation, and the fluorescence lifetime measurement is available technique in the analysis of multi-component sample containing analytes with overlapping fluorescence bands. We discuss about the different types of fluorophores present in are used. So these are the extrinsic fluorophores, which having aromatic ring, have a potential for increased extended conjugation, and at least one electron donating group such as OH, NH2 attached to the aromatic ring. You can see here the structure of fluorescein, which is having fluorescence properties, but once it is forming a bond or cyclized, then it loses its fluorescent properties. This is the list of different fluorophores used in the biology and chemistry, and its excitation wavelength as well as emission wavelength are given here in detail. You can read here. We discuss about the intrinsic fluorophores. These are the some biomolecules having its own intrinsic fluorophore that are the fluorescent themselves. The amino acid with aromatic groups such as phenylalanine, tyrosine, tryptophan are fluorescents. Hence, protein containing these amino acid have an intrinsic fluorescence. The purine and pyrimidine bases of some of enzyme, for example NAD and FAD, are also intrinsic fluorescence. Intrinsic fluorescence is used to study protein conformation, changes to be probed for the location of active site and coenzyme. You can see here the absorption and fluorescence properties of the all three amino acid, and along with their fluorescence lifetime is given here. And here you see the structure of the NADH or FAD, which are the also intrinsic fluorophores. As I discussed that fluorophores are of two types. One are the intrinsic fluorescence because of its own chemical nature of the molecules which are under investigation, and the other are fluorescent molecules which are added to the biological system or any other system to investigate its structure, property and anything. These are known as extrinsic fluorescence, which has been used to study the binding of, for example, it is used to study the binding of fatty acid in serum albumin, to characterize number of binding sites in any for a cofactor substrate in enzyme molecules, and to study the small molecule interaction to the DNA double helix. For example, you can see several molecules which are used as a extrinsic fluorescence to characterize the biomolecules, like rhodamine, which is a well-known fluorescent molecule and widely used for the detection of biological system in the biological system. Then fluorescein, coumarin, carboxycyanine dye, aromatic hydrocarbon and its derivative, pyrene, pyridine, anthracene. These are the well-known fluorophores, extrinsic fluorophore molecules which are attached to the to investigate or detect a lot of biochemical reactions and biochemical processes. The other important component of the spectrophlorometer, although it's not the part of the spectrophlorometer but it is used for the study, that's the cuvette. It should be a fluorescence cuvette or of a special type of cuvette, and it have 4 transient site, and it is made up of the quartz generally, but maybe of the glass, but quartz cuvette is preferred because of the very low absorbance and the other advanced features. When the excited light impinges on the sample, molecules in the solution are excited and some of the light is emitted, and the emitted light are right angle to the incoming beam, and it is analyzed by the emission monochromator, which actually select the light and directed it to the detector. The wavelength analysis of the emitted light used out by measuring the intensity of fluorescence at pre-selected wavelength. The analyzer monochromator directs emitted light of the pre-selected wavelength to the detector. Photomultiplier tubes serve as a detector to measure the intensity of the light, because the light quantity is very low, so of course the photomultiplier tube help you to multiply the light and give you a proper amount of signal, and the output current of the photomultiplier is fed to some measuring device that indicates the extent of fluorescence in the form of signal or in the form of fluorescence spectrum. We give the example of some naturally occurring fluorescent organic compounds, and such as naphthalene, and it's having the emission range in the 300 to 365, anthracene having 370 to 460. Like that, you can see the emission properties, emission range of all the compounds used in the fluorescent organic compounds. Now we discuss what are the structural factors which affecting the fluorescence phenomena or fluorescence spectrum. Because by the fluorescence you may get the information about the structural properties of any molecules under investigation, of course, especially used for the studying the structural properties of the biological macromolecules. So fluorescence is expected in molecules that are aromatic and multiple conjugated double bonds with high degree of resonance. So only those molecules have fluorescence tendency which have high number of pi electrons, which can easily absorb the light and get excited by absorbing the light. Generally it doesn't happen with the sigma electrons, only the pi electrons are involved in the fluorescence, and it is expected in polycyclic aromatic system, because in the polycyclic aromatic system a resonance can easily occur, and in the resonance, because of the resonance, fluorescence phenomena can be observed. So these fluorescence property of the molecule is actually affected by so many variables, so many properties, like substituent such as amino group, attachment of NH3 group, attachment of OH group, attachment of fluoride, attachment of carbonyl, attachment of NHCH3, attachment of secondary amine, like that often enhance the fluorescence, because these species are rich in electron, and that induces more and more resonance. That's what the fluorescence property of the molecule is increased by addition of these kind of group to the aromatic ring of the molecule. On the other hand, there are certain group which decrease the fluorescence intensity or quench the fluorescence intensity, like chloride, bromide, iodide, then NHCO, CH3, nitrate, and COH group. These are the mostly electron withdrawing group, which or highly electronegative group, which causes the decrease in the fluorescence intensity. The another important factor is the molecular rigidity. Increase in the molecular rigidity enhances the fluorescence property of the molecule. Then that's what the substances fluoresce more brightly as in a glassy state or in viscous solution. And the formation of chelate with the metal ion also promotes fluorescence. So these are the certain factors which enhancing the or which affecting the fluorescence. Then the introduction of paramagnetic ions give rise to phosphorescence but not fluorescence in the metal complexes. And at last, change in the system pH may also affect the fluorescence, because by changing the charge state of the component may affected, and that's what the delocalization of electron is affected, and thus the fluorescence intensity are greatly affected by change in pH of the system. As factors that affecting the fluorescent properties of a molecule, you can see that there are typical aromatic compounds like pyridine, furan, thiopene and pyrrole. They don't have fluorescence properties. However, the other aromatic compounds that fluoresce are quinoline, isoquinoline and indole. Similarly, effect of molecular rigidity on quantum yield. The fluorine molecule is held rigid by central atom. Two benzene ring in biphenyl can rotate to one another. You can see here that fluorine is the structurally more rigid as compared to biphenyl. That's what it is showing fluorescence, but biphenyl doesn't. Similarly, free 8-hydroxyquinoline molecule in solution are easily deactivated through collision with the solvent molecule and do not fluoresce. Rigidity of zinc 8-hydroxyquinoline complex enhances the fluorescence. So the molecular rigidity in any molecule enhances the fluorescence intensity of the molecule. We discussed that the substitution effect on the fluorescence of benzene. You can see here is a very important slide showing that alkyl group doesn't causes any change in the fluorescence. However, OH groups, methyl group, OCH2 C2H5 group causes decrease in fluorescence wavelength, and however the intensity of fluorescence increases. Carboxylic acid group again decreases the fluorescence wavelength, but a large decrease is observed in the fluorescence intensity. Similarly, amino group, amide and primary, secondary and tertiary amine decreases the fluorescence wavelength and increases the fluorescence intensity. However, nitro group doesn't have any impact on the fluorescence shift, but it causes total quenching also, so decrease in fluorescence intensity is observed. Cyano group doesn't affect causes any change in the wavelength, but it increases the fluorescence intensity. However, thiol group causes decrease in both wavelength as well as intensity. Chloride, bromide, iodide and fluoride causes decrease in wavelength from fluorine to iodine and increase in the intensity from fluorine to iodine. We discuss about the fluorescent effect of environment on the fluorescence, and the first parameter is the temperature. A rise in temperature almost always accompanied by a decrease in fluorescence intensity, because the greater frequency of collision between the molecule increases the probability of deactivation by internal conversion and vibrational relaxation. You can see here in the diagram that as the temperature increases, a decrease in fluorescence intensity is observed from 25 degree to 60 degrees Celsius. Fluorescence are greatly affected by the environment. That's what it is used to investigate the environment, a change in environment of any biological molecules. So for example, pH, as I already discussed, that the pH influences the ionization state, and that's what it changes the conjugation property and aromaticity of compound, and that's what it affects the fluorescence. The other is the solvent also affect the fluorescence through their ability to stabilize ground state and excited state differentially, thereby changing the probability and energy of both absorption and emission. Another property is the dissolved oxygen, which often decreases the fluorescence intensity dramatically and an interference in the many fluorometric method. Then molecular oxygen in paramagnetic, especially singlet ground state, which promotes intersystem conversion, crossing from singlet to triplet state in the molecule. Longer the lifetime of the triplet state increases, the opportunity of radiation-less deactivation can occur. Other paramagnetic substances, including most transition metal, exhibits the same effect. We discuss about the solvent effect. General solvent effect: fluorescence depends on the polarizability of the solvent, and increase in the dielectric constant of the solvent usually shift fluorescence to higher wavelength. You can see here in the graph that the fluorescence maxima of the organic solvent is shifted drastically to the higher wavelength once it is replaced by the water molecule which having the higher dielectric constant, and of course the polar interaction, lower energy of excited state, stabilize the excited state. Now we discuss the inner filter effect. At low concentration of the emission of light is uniform from the front to back of the sample of cuvette. At high concentration, more light is emitted from the front than the back. Since the emitted light only from the middle of the cuvette is detected, and the concentration must be low to assure that the fluorescence measurement. We discuss about the quenching. Quenching is simply defined as the loss of energy by interacting with the different molecules in the nearby. Only a proportion of light is absorbed and is emitted as radiation. Energy may be lost in vibrational transition and heat transfer with the solvent as well. To further process, we can diminish amount of light energy emitted from the sample. Internal quenching due to intrinsic structural features, example structural arrangement. However, the extrinsic quenching, interaction of the excited molecule with the another molecule in the sample, or absorption of excited or emitted light by another chromophore in the sample. All forms of quenching results in a non-radiative loss of energy. We discuss about the quenching. Quenching decreases in fluorescence intensity due to a specific effect of the constituent of solution, example concentration, pH, pressure, and chemical substances. There are different types of quenching: self-quenching, chemical quenching, static quenching, collisional quenching, and the chemicals which affect, that's the pH, heavy metals, halide, etc. Now we discuss most important part of the fluorescence spectroscopy, that whatever the output you get, it is in the form of fluorescence spectrum. So how to analyze or how to interpret the fluorescence spectra? So you keep some rule in the mind that all fluorescence of the protein is due to tryptophan, tyrosine, and phenylalanine unless it contains some extrinsic fluorescence or cofactor. The lambda max of tryptophan shift to shorter wavelength, and intensity of lambda max increases as the polarity of solvent decreases. If the lambda max is shifted to the shorter wavelength when the protein is in a polar solvent, and tryptophan must be internal. If the lambda max is shifted to shorter wavelength with the of a protein in a non-polar solvent, tryptophan on the surface of the protein, and conformational change in such that it brought to the surface. If a quencher such as iodide, nitrate ion quenches tryptophan fluorescence, it must be on the surface of the protein. Failure to do so, it means that it is either internal to the protein or is in the highly charged region. Tryptophan fluorescence is quenched by neighboring protonated acid group also. If the pK measuring by monitoring tryptophan fluorescence is the same as the pK of the non-ionizable group, for example carboxyl group, then the group must be near to the tryptophan. And if a substance that affect the quantum yield of the free amino acid doesn't affect the fluorescence of the protein, it must be so by producing the conformational changes in the protein. And last, if a substance bind to protein, tryptofluorescence is quenched, either is a conformational changes or result of binding or tryptophan near the binding sites. So these are the rule has to be remembered. We talk about the common problems associated with the fluorescence measurement. Sometimes the reference material is fluorescent as the sample, and contaminating substances which causes Raman scattering or Rayleigh scattering. Fluorescence reading is not stable, fogging of the cuvette when the content is much colder than the ambient temperature, drop of liquid on the external face of the cuvette, light passing through the meniscus of the sample, bubbles forming solution as it warms, quenchers such as molecular oxygen, or sometimes sensitivity is inadequate. Now we discuss about the applications of fluorescence. Fluorescence is the most widely used technique. It can be applied to the direct measurement such as metal cation as a fluorescence chelate, for the indirect measurement where the fluorescence of trends being determined is measured prior to after the quenching. Then indirect measurement, where the fluorescence of the determined substance is enhanced by the addition of reacting materials. It is also used for the tracer technique, for the bioengineering analysis, for the fluorescent in situ hybridization fish, and for spectral fluorescence signature. So students, let's now summarize what we all have learned in this module. Fluorescence is a cyclic process and only a portion of the energy is absorbed and re-emitted as a light. Emitted light is of lower wavelength, lower energy and longer wavelength than absorbed energy. The basis spectrophotometer contains light source, 2 monochromator, a sample holder and a detector. And emission spectrum monitors the fluorescence intensity at a constant excitation wavelength, and excitation spectrum monitors fluorescence intensity at different excitation wavelength, holding the emission wavelength constant. In proteins, 3 amino acids like tryptophan, tyrosine and valine acts as an intrinsic fluorescence, and quantum yield is the ratio of photon emitted to the photon emitted to the photon absorbed by the system. And finally, the change in temperature, pH, solvent affects the environment of chromophore and thus influence the fluorescence. Thank you.